Log on, tune in, find out. Another good idea from Cambridge.
Miguel Tierz from Brandeis University, who will talk on Stieltjes-Wigert polynomials and quantum topological invariants.
Okay. First of all, thanks to the organizers for allowing me to speak and to give a talk in this very interesting workshop. I'm going to be talking about this precise orthogonal polynomials named Stieltjes-Wigert, and I will try to explain how they are useful to compute certain type of topological invariants. This connection is possible due to description of gauge theory in three dimensions, which is topological. This gauge theory is called the Chern-Simons theory, and the observables of this theory are known to be topological invariants. And what is interesting is that in recent years it has been shown that this theory, at least for certain manifolds, can be described in terms of models of random matrices. Then these random matrices are solvable with the orthogonal polynomial technique, and this is why there is a connection between these two things. Okay. Let me begin by telling you how I plan to organize the talk. I will very briefly introduce random matrix theory, just giving the main definitions, and then discussing the orthogonal polynomial method, which is central to random matrix theory in general, and in particular in the type of models I will consider. Then, extremely quickly, just to tell you what is Chern-Simons theory. I'll just say the minimal thing, otherwise there is no time. And the important thing is to show you that there are random matrix models that describes certain types of this gauge theory. Okay. Then at the practical level, since these random matrices have a well-defined system of orthogonal polynomials that solve them, which will be the Stieltjes-Wigert polynomials. These are orthogonal polynomials which are orthogonal to a log normal distribution instead of, for example, the simplest, more well-known cases like a Gaussian distribution, which give Hermite polynomials, etc. And this, I will give you simple computations. The most simple one is that this is called the Witten-Roche-Tikin-Turaev invariant, which is the partition function of the Chern-Simons theory, is computed with Stieltjes-Wigert polynomials directly. Then a more complicated invariant called the quantum dimensions will be also computed with the same polynomials, but then it's not so direct like the first one. So things get difficult quite fast, but analytical computations are possible, and I will show the results. Okay. Then, since the title of the workshop is discrete systems and special functions, I will show you that the model that that will appear here, which is a continuous model, can be discretized while keeping its meaning intact. I mean, in particular, all the Chern-Simons meaning of the model is completely unchanged if you discretize the model. And this will be possible just applying the classical moment problem, because the moment problem associated to these orthogonal polynomials, and this is known since Stieltjes actually, is undetermined. Okay. So if there is time, I will also talk a little bit about the orthogonalization version of the Stieltjes-Wigert model, and how it's necessary if you want to compute a more complex invariance. And if also a little bit, maybe very briefly, to mention that there is a connection with one-dimensional exactly solvable models, which are not well known. These models will be related to Kalodger and Söderholm models, but apparently have not been studied in the literature, and they are extremely related, directly related to the random matrix description of Chern-Simons theory. One open problem here is that the model is known to be exactly solvable, but integrability has not been proved, so that's an interesting open problem. Okay, and I will finish with conclusions and outlook. Okay. So first of all, random matrices. This is the main definition. This is the probability distribution that is postulated for square n by n random matrices with random distributed elements. H. Here this beta parameter is central. I will mention what it's about. And the most well-known model, the first one introduced, is the Gaussian model, which has here a quadratic polynomial. If this is the case, if you have here a quadratic a quadratic polynomial, then we have statistical independence of the matrix elements of the random matrix ensemble. But this is not the kind of model at all we are going to discuss, but this is the simplest one. And then the beta parameter, which typically is 1, 2, or 4, it depends on the symmetry of the ensemble. So the ensembles of n by n random matrices are defined by the following. We have this probability distribution we have shown before in the space of matrices, and we expect it to be invariant under any transformation that can be of 3 types: of orthogonal transformation, beta equal 1, unitary transformation for Hermitian matrices, or symplectic for quaternion self-dual matrices, beta equal 4. The case I will mainly be studying is corresponds to beta equal 2, which corresponds to Hermitian matrices, which luckily enough is the one that is easier to solve analytically. And as I said before, the matrix elements which are not related by the symmetry of the matrix are statistical independent, then we have Gaussian ensembles. But at the practical level, nobody works with in the space of matrices, it's not practical. So we have the diagonalization property, and for each matrix X, there is a matrix U that maps it into the space of eigenvalues. So the price you have to pay is the Jacobian of the transformation, which is the usual van der Monde determinant, raised to a power of beta, which is depending on the symmetry, as I said before. As I said, we will be discussing beta equal 2, and the model I will be dealing with will have a log square potential. So the weight function, which is this term here, will be a log normal, the log normal shape. I mean, that's like the exponential of a Gaussian, essentially. So that would be this is the central model, and this is the model that will appear in the simplest Chern-Simons theory that I will show in a few slides. So typically at the practical level, then, models of random matrices, you begin dealing with this n-dimensional probability distribution, and you are interested in the n partial integrations over this n-dimensional probability distribution function. If you integrate over all the variables, then you have the normalization constant or partition function in the physics literature. You integrate over all except 1, this is the density of states. You integrate over all except 2, then you have the 2-point correlation function. And what is interesting about the orthogonal polynomials method is that if you know the orthogonal polynomials associated to the weight here, which is not always the case, of course, then you have this powerful result which tells you that any correlation function can be computed if you know the orthogonal polynomials, because if you know the orthogonal polynomials, you can construct this object here, which is a 2-point kernel, and the definition is here. This is the weight function, and these are the orthogonal polynomials. Okay. A more explicit expression, you apply here the Christoffel-Darboux identity, and then you have this expression here. So knowing the orthogonal polynomials puts you on the right track. And fortunately, the model that appears in this kind of gauge theories that I'm considering has a well-defined orthogonal polynomials. Okay, so very briefly, now I'll talk about Chern-Simons theory. Chern-Simons theory is a topological quantum field theory of 3 dimensions. Associated has a gauge group associated G, and this is the main definition of the action. So this is a 3-form you have here, and A is a connection on the manifold. So this is the action, and what's interesting about this theory, well, it appears in many different subjects within physics, and most of the people who has paid attention to the developments I'm showing you is on string theory people, because this theory is related to topological string theory, but I won't talk about it. But the Stieltjes-Wigert polynomials are useful then to compute analytical expressions in this theory, and that's because of the connection with the Chern-Simons. It also appears in condensed matter physics, etc. But in mathematics, it's well known because Witten showed in 1989 that the observables associated to this theory, the simplest being the partition function, define a topological invariant. That was interesting because it connected with results of important results in topology, like the Jones polynomial, and give rise to a new type of topological invariants. They are called typically quantum topological invariants because they have a quantum group symmetry associated to them. Some of them were new, and some of them allowed to explain all results in topology. So it's still, so not only physicists have studied this theory, but mathematicians as well. And before I told you about the partition functions called the Witten-Reshetikhin-Turaev in the mathematics literature, because then just very shortly after Witten did his seminal work, then Reshetikhin-Turaev, because this is based on path integrals, so this is highly non-rigorous. So Witten got the Fields Medal, but it's with non-rigorous methods. And then Reshetikhin and Turaev, using quantum techniques from quantum groups, gave an equivalent description which coincides with this one, which was completely rigorous. Okay. So the main result that was done by Marcos Marinho in 2004, this paper, is that the partition function of Chern-Simons theory for a certain type of manifold is a safer manifolds, I should have written it here, which are central in three-dimensional topology. He showed that the partition function can be expressed with this. This is based, actually, this result was a combination of 10 years of work of many people. And so, because typically the methods developed by Witten are based on Wess-Luminow-Witten models, conformal field theory, very complex sums. So these results comes from using these complex sums by Witten and applying complex analysis is showing that for certain manifolds, these sums can be expressed as integrals. And these are the integrals. And if we pay attention to the simplest case, which is the three-sphere and the gauge group, the unitary gauge group, then we have this very simple expression, which looks very much random matrix-like. The dimension of this, it's n, which coincides with the rank of the gauge group. And so this paper finished with this expression, and so they finished with n-dimensional integral expressions for these Chern-Simons partition functions. And that was it. So the method to arrive here is quite involved and using a lot of complex analysis. So it would be good, to check, because this expression is known using in the paper by Witten he gave expression for this based on these conformal field theory techniques. So to make sure that this is correct, it will be interesting to do this integral. So the rest of the talk mainly is discuss this fact, to compute these n-dimensional integrals and some more difficult that appear. So this model is in random matrix theory, but it was not studied with exception of a paper by Peter Forrester in '89, which is the same year as Witten published his paper. Not a very well-known paper, but he did most of the analytics necessary to compute it. That was in a totally different context, in the context of non-intersecting random walkers, vicious random walks, it's called in physics. And basically what you have to do, because this is very similar, you see, as a Gaussian ensemble in random matrix theory, except for the fact that you have, instead of the van der Monde determinant, you have the Gaussian factor here. You have, with a large separation of the eigenvalues, you have the interaction term, which is exponentiated. So it's a much more fluctuating model, but you see it's very similar to a Gaussian ensemble. So the idea is to make a change of variables. Then you trade this if you want to have, because all the orthogonal polynomial techniques are known, can be applied if you have a standard van der Monde term here. So this is what we have to do. We want a standard van der Monde term, and the price to pay is that you change the Gaussian for a log normal, because you have exponentiation here. This log normal has nice symmetry properties, which are explained here. This is actually the Q-Persson equation associated to the log normal weight. And just doing this very simple trick, you have the partition function then can be expressed on this. This is standard random matrix expression. So you only have to know the orthogonal polynomials associated to this way. These are very well known, and they are called Stieltjes-Wigert. Stieltjes discussed it in the moment problem in 1894 in his posthum memoir, the non-uniqueness of this function. I will explain what it means in a few slides. And then Wigert in 1924, computed the orthogonal polynomial. So they are very old, and you can find this in Sego book, for example. So it's nothing really very exotic for the people who is not on the orthogonal polynomials business. So for the partition function, we only need actually the leading coefficients of the polynomials. And this is old result from the 70s in random matrix theory. The partition function, you only need the leading coefficients. So we apply and we have here the Stieltjes-Wigert partition function is this, and then we just have to relate it now to Chern-Simons theory. This is in the original model I showed before, the n-dimensional integral that I showed before. And sorry, let me go back and show you, because here we have the coefficient here, this GS in physics would be the string coupling constant. Now, this is the parameter that appears in Chern-Simons theory. So the Q parameter here, let me bring it. Okay, we have the weight is like this, 2GS. Then the Q parameter is this is the definition for it. Okay, so that's it. And interestingly enough, the way that playing with your Stieltjes-Wigert polynomials, the Q parameter turns out to be the Q parameter that you find in Chern-Simons theory or in topological string theory. So everything is consistent. Then for Chern-Simons theory, the G sub S is 2pi. So, and this is the typical coefficient that in the Chern-Simons action. So this is the parameter. And this n is the rank of the gauge group. So with the Stieltjes-Wigert polynomials, we found this expression, which is well known in Chern-Simons theory, and we found exactly so it is contained in Chern-Simons partition function. It's contained. It can be computed with this Stieltjes-Wigert polynomials. That got interested many people in topological string theory in these polynomials, because this is the simplest case. This is a simple quantity, but for them it was very relevant to show that because the partition function is directly related to the free energy, and they could show that this free energy is the same as in a topological string theory. So this is a case which is known already by other techniques, but for more difficult objects, the Stieltjes-Wigert may be the only analytical way to compute this object. So this is why people in this area got quite interested about it. However, the bad thing is that then things got very difficult quite easily. So I said I wanted to talk a bit about discretization, so just showing you the result that I did here with Sebastián de Haro a few years ago. Since the moment problem associated to the log normal weight is undetermined, which means that there are many deformations infinitely many deformations of this weight that leads to the same orthogonal polynomials. And as we have seen, the orthogonal polynomials is what fixes the quantities we're interested in. In random matrix quantities, you see they have a van der Monde determinant. Only the integer moments play a role in any quantity compute in the partition function, etc. So we could apply the all well-known results in classical moment problem to find a discrete version of the model I showed you before. And so I think that's the first case where that the log normal was undetermined was known since Stieltjes, as I said before. But explicit expression for the discrete weight was given by Chihara in the 70s. And this is the explicit expression, which is essentially a discretization of the log normal. So applying this to the matrix model, we found that there is an equivalent model which is completely discrete, and the partition function of this guy is going to be exactly the same. This was a mathematical result that we published here, and then some people studying Q deformation of a 2D Yang-Mills theory found this discrete model more useful and more relevant to the gauge theory, and then they studied, and they began also to study the Stieltjes-Wigert polynomials. So that was mainly, just to see more properties of this random matrix ensemble, which is different from the classical cases like the Gaussian, which is solved with Hermite polynomials. So, but it was finally found use in gauge theory. So more difficult, now I want to tell you how things get more difficult very easily. Because when we want to compute some observables in Chern-Simons theory which are more complex than the mere partition function, then we end up with expressions. I give you the more compact version within matrix space. As soon as in Chern-Simons, the partition function is the integration over the action I showed before. But if you want to study more complex observables, you have to put what is called Wilson loops into the action, into the path integral, sorry. And Wilson loops are the holonomy of a loop that you put into the manifold. So the simplest case is when you put the loop is what they call the unknot, and you put a circle into the S3 manifold, and then you do the path integral. If you do this, it's well known that you find one object called the quantum dimensions. And they are called quantum dimensions because they are the Q-deformed version of the dimension of a representation of the gauge group. So it's also, we also have integral random matrix-like integral expressions for this case when you have a circle in your path integral, and then the Stieltjes-Wigert model gets modified by the introduction of a sure polynomial here. So this is much more difficult then, because in random matrix theory there are very little there are not many computations of insertions of sure polynomials in the random matrix quantity. So, but we managed to do this with a mixture of the Stieltjes-Wigert polynomials and some combinatoric tricks, because you have representation theory here through the sure polynomial. And we did this computation, and we found that it was equal to the quantum dimensions. This is the Casimir of the UN gauge group and associated with the representation lambda, because here the lambda, this random representation is typically given by a Young tableau. So we'll have something like that for or whatever. Okay, so then we have to do this for any lambda, for any representation. That's much more difficult than the partition function computation. And we did it with Jacinto Olive in the Journal of Mathematical Physics. Okay, so that's the next step. There are not many more that I have been able to compute. Another thing that we did in the same paper is to construct a biorthogonal version of the random matrix model, which you remember here we had a square here, because I always said that we deal with Hermitian. But as soon as I want to study another manifold instead of S3, then we have to deal with this guy instead of the Hermitian with the square term here. Again, this is difficult, more difficult than the usual, because you need to know the biorthogonal versions of the Stieltjes-Wigert polynomials. I didn't find them on the literature, but very related polynomials were studied. So I used these Kirchhoff-Hauser polynomials, which were studied by Al-Salam and Berma in '83, I think, and applied a limit that reduced the Q-Laguerre polynomials, because these are the biorthogonal Q-Laguerre, which somehow must include my polynomials, and applying the same trick that reduces the Q-Laguerre polynomials. This was shown by ASCII in the '86, I think, to Stieltjes-Wigert. We managed to find the system of biorthogonal polynomials, and then again to solve and to compute this object. Okay. So very differently, I want just to say that this model is also related with one-dimensional exactly solvable models. Here I brought the case of the very well-known case of the Calogero model, which is associated to you see the ground state wave function of the Calogero model. So you have n particles interacting in one dimension with two body terms of this type. The ground state wave function of this Hamiltonian, turns out it coincides with the probability distribution function of a Gaussian random matrix ensemble. It's explained here, the Wigner-Dyson distribution, which is the name for the Gaussian ensembles of eigenvalues, coincides with the probability distribution of the n-particle coordinates of the quantum ground state of a one-dimensional Hamiltonian. Okay, if you look at the literature, and my question was, does the same result applies to the Chern-Simons matrix model, which, if you remember, had here a sine hyperbolic? And you look at the literature, they give a list of all the possibilities of one-dimensional Hamiltonians with the Hamiltonians in the corresponding ground state, and it's not there. But again, in a paper by Peter Forrester, we find a counterexample, and he found that the Hamiltonian for the model with the sine hyperbolic is given by this guy. So we have this additional two-body interacting term. You see, this is the trivial modification before to the sine hyperbolic case, but these additional correlations have to be taken into account. And in some later work, which is largely unknown, it is shown why this happens studying the functional equations, and a new set of models are generated, and one of them, the Chern-Simons model, is included in a new set. What I found interesting about this is that this model is not studied at all, and of course it's 100% related to physics, because it's the Chern-Simons matrix model. For example, it's the normalization constant of the ground state wave function is a physics partition function. So And for example, one property, this guy showed that exact solvability, but integrability is not studied. So I wonder whether a Lax pair exists for this model. Okay, so here in this more recent work I did, well, we did the same but for other gauge groups. This is always for the UN. Here I studied for the orthogonal and symplectic groups. And I studied some physics aspects of this exactly solvable model, and I showed that it related with free fermions at finite temperature. But this is more a physics applications of the model, interpretation of the model. So let me conclude with a summary of what I said so far. That Chern-Simons theory on certain manifolds admits a description of terms in terms of random matrix models. One interesting thing of this Chern-Simons theory is that the observables are quantum topological invariants. This is interesting nowadays in topology, also in quantum computation, etc. We studied in detail the simplest case, which is when the manifold is a 3-sphere, which is the simplest Chern-Simons theory possible. And then the corresponding matrix model is solved analytical with Stieltjes-Wigert polynomials, which are the polynomials associated to this weight. The partition function is computed, but more complex invariants are not so easy. And we have done the next case in difficulty, which is when you have this loop in the path integral, and then it's this, you have averages of sure polynomials in the random matrix distribution. So then things got already much more difficult very fast. But this case we still managed to compute and found the consistency that indeed it relates to quantum dimensions, which is not obvious that. So this gives strength to the random matrix description of Chern-Simons theory, because you want to do things explicitly. Then we also studied the orthogonal version of the models. It is required to introduce the polynomials because they were not in the literature, although that was because the orthogonal Q-Laguerre were there, so that was quite easy. And then I mentioned this connection with these one-dimensional cyclically solvable models that are related to Calogero and Sutherland models. And integrability is an open problem because almost nothing is known about this, mathematically, about these exactly solvable models. And if you see, you remember the Sutherland model is the interaction with on a circle with sign, you have just this. So the model, if you want to consider, there is a hyperbolic version of this, which is, okay, not trivial the past, but so my model is essentially has a Gaussian factor into the wave function additional. And this is still, you can explain this additional Gaussian factor with this additional correlation terms in the Hamiltonian with the two-body term. And so it's a direct extension of very well-known models, but many properties are not known, like most importantly, the integrability. I think that's it.
You mentioned the Q-Cohnhauser polynomials.
How are they defined? I'm not familiar with them.
Okay, they are defined. Yeah, I think let me check my own paper because I don't remember very well. Yeah, the Q-Cohnhauser was done in a paper. Let me see the reference. The Al-Salam can give you the reference first. Al-Salam and Berman. It was here. Just a minute. I'll tell you the weight. Yeah. They are the orthogonal version of the Q-Laguerre.
Yeah.
Okay, so yeah, I can give you here. So let me see. Yeah, we consider the normalized Q-Laguerre measure, which again is an undetermined moment problem, so you have others. But for the practical computation of the polynomials, you just maybe need one. Okay, this is prefactor. And then we have well, this is the usual Q-deform number. Okay, so this is the Q-Laguerre measure, and then the B-orthogonal are the polynomials which are orthogonal to. I can give you the expression, it's rather large. But let me also give you the reference. I have copies of it. Okay.
How does this bi-orthogonality come out? It's just the polynomials in one variable that you get something bi-orthogonal? How
Yeah.
does that work?
Yeah.
Or do you need iteration of functions?
Mm-hmm.
So I don't you don't have to give explicit expressions. It's not the idea about getting bi-orthogonality.
Yeah. By orthogonality, if I remember correctly, because this I did some time ago, you have here one set of polynomials. Okay. These are the moments, and then the other set. Okay. Okay. So. Yeah. Oh yeah, sorry. Yeah, I kind of, because this I did a couple of years ago. So yeah, that's the definition. Yeah, I was going right. So here. Okay. You have two sets of polynomials, and one has the usual orthogonality property, and the other has the same but with monomials which modify by a parameter here. This is to take into account the fact that you don't have a Vandermonde here, but you have something like that. Okay, with theta as a parameter here. Okay, I was using k all the time. And I think Alexei Borodin studied in 98 paper random matrix ensembles for this be orthogonal, but for the classical models, the Hermite, Laguerre, and Jacobi. And this is for the Stieltjes-Wigert. So that's what you have. Two sets of polynomials, and this is the. Okay. And if this also satisfies that theta n and E m, then they have. Okay, so it always depends on this k additional, because you have here this k. In the orthogonal case, you would have, okay, you only have this, the first condition. Okay? I wrote it twice. So that's the idea mainly. You have this instead of only one, and that's they should be orthogonal. This means that they satisfy this, and the coefficient here depends on the k that you have here. So this is the parameter, and the k is the parameter that you have here. And okay, so that's a bit orthogonal.
Thanks. Let's thank our speaker and in fact all the speakers of this.